I'm Ryan Grabowski, a Embry-Riddle robotics student. Here's a PLC project I created for this PLC class with Dr. Andalibi. It's running on a S7-1200 PLC from Siemens, along with an HMI. The idea of this project is to emulate a sort of semi-industrial water tank mixing type station. So there's two water tanks here, the green ones. Those are the storage tanks. The two green water tanks right here are the holding tanks for the system, and then the pink one is going to be the overall mixing tank. And each of these tank assemblies have two sensors each, two float switches. One will indicate to the program when the water level is high, and one for when the water level is low. This is useful for the overall program because it tells us when our pumps can be on and off, so we don't overflow tanks and destroy pumps by running them without water. So as I mentioned, the bottom float switches are to ensure that the motors do not run without water. Those motors that I'm mentioning are on the bottom of the acrylic plate here. Those are also controlled with the HMI through the relay board over 12 volts, and the control signals are 24 volts. And then also to control the direction of the water coming back from the pink mixing tank, we have two 24 volt solenoid valves also controlled through the HMI. And finally, for the mixing tank, there is a stirrer motor. And for the user to actually control all of this, they're going to use it all from the HMI. So on the HMI, you can turn on and off all three motors, the mixer mixing stick, through the stepper motor, of course. And for the mixer pump, there's two modes you can go in, the solvent route or the solute route, which is what we call our two holding tanks. And when you enable those, it's going to open and close the solenoid valve, choosing where the returning water goes to. And as you can see in the video, some lights are flashing right now. That's our limit switches. So when the tank is low level, for example with the solute pump, the actual pump will not turn on. Same with the mixer tank. Because the water level is low, it's not safe to run the pump. With the solvent pump, there's no indicator on the solvent tank, and the mixer tank is not high. So if I hit that, it will turn on. Should be able to briefly hear that in the video.
Yeah, you see the water is coming up.
Mm-hmm. And now it just shut off by itself. And that's because if we look back at the HMI, the solvent tank is now at a low level, or it was at the low level briefly, just because of the fluctuating water levels. But since it's no longer at a low level, I'll be able to turn it back on, and it should turn back off nearly instantly. Yep, so now you can see that blinking low level light, which was on there briefly. So now I can put more water into the solute tank from the mixer tank using this set of controls to the right. And that's going to operate until either the solute tank becomes high or the mixer tank becomes low. And the mixer tank became low, which you can indicate by the blinking red light right there. So another functionality we have for this is the mixing tank has a mixer. So if we hit this mixer button, it will turn on the stepper motor, and inside the big red tank, it is being stirred with a mixer. And that stepper motor on top is controlled by a stepper driver over there under the PLC.
This one here. Okay.
Yep, that's the important parts of the system.
Okay. So, Ryan, what would you say, how much time roughly out of, because this team has two members, and right now only Ryan is here, but if you would just want to give us a rough estimate of how much time making a system like this took you and your teammate, what would you say? Rough.
So building everything, 3D printing the mechanicals just for the visuals and like holding the water, I would say it took around 20 to 30 hours just getting it right, making sure our connections worked right and didn't leak. That could be reduced by making correct decisions the first time with choosing of epoxies and sealants. And then coding wise, I'd say it was another 30 to 50 hours just setting up the PLCs from scratch and wiring everything, doing trial and error to figure out how it's supposed to be programmed.
And what would you say about the cost of anything besides the PLC and the PLC system? Roughly how much would it cost?
So all of our custom components are 3D printed. So that would be $20 spool of PLA. We have our tanks are three sparkling water bottles. So that's $2 a tank, so $6. Epoxy holds in our tubing, another $8. So that puts us at about 50. And the tubing.
So the total, let's say the total roughly, is that more than $500?
Everything but the aluminum should be under 200.
Under 200. So basically, this thing, if you include aluminum, should be about 1,500, right?
Yes.
Something like that. Definitely below 2,000.
Including the PLC at 1,500. Aluminum shouldn't be.
Yeah, I mean everything should not exceed $2,000.
No way.
Okay, so by no means this system will exceed $2,000, and this is a fluid control system that is kind of resembling what you see in chemical reactors, mixing and control on the fluid level and everything, fully automated by the Siemens S7-1200, and a very good HMI developed by all the work. Again, if you want a system like this from a vendor, you're looking into way more than 10 grand to get it all made and delivered to you. But again, thanks to our, I would say, almost graduating students right now, they are making this great system for our future PLC and automation class at a cost way below $2,000. So I really need to appreciate all that Ryan and Ben did in this amazing project. And thank you so much for watching this video.